Welcome to physics class on electricity, part 2 of class 10. In the previous video, we have done about that electricity part 1 of 2, class 10. There I have discussed in depth about the electric current, electric circuits, then electric potential difference, and then about the circuit diagrams, the symbols to be used of the components in the electric circuit, and Ohm's law and its verification. So for today we will start from the remaining parts of the electricity, that is starting from resistance, factors affecting this resistance, and then a combination of resistors in series and in parallel, and then heating effect of electric current, electric energy and electric power. All those things we will have to discuss in this new video, okay, second part of 2.
What is this resistance? Resistance is a property of a conductor which opposes or resists to the flow of current through it. What is this opposing? Now you know that in the current inside the conductor, electrons are moving or flowing, right? This motion of flow of electron is opposed inside the conductor. This is an inherent property of that material, okay, or conductor. This property of resisting the flow of current or a flow of free electrons in it, we call it that as resistance. So according to that Ohm's law, R will be equal to V by I, because V is equal to IR. When you cross multiply it, you will get it what? Your V will be equal to IR, right? So your R will be equal to V divided by I. So the SI unit of resistance is what? Ohm, and it is denoted by omega like this. Got it? Omega. Clear? Have you seen? Yes, omega. So your 1 omega will be equal to what? 1 volt. SI unit of potential difference is 1 volt. SI unit of current is ampere. So your 1 ohm will be equivalent to 1 volt per ampere. Got it? Now, next, let's try to define it. What is 1 ohm resistance? Okay, 1 ohm resistance is that resistance which, when maintain a potential difference of 1 volt at the two ends of the conductor, and if the current flowing through it is of 1 ampere, then the resistance of such conductor or material is said to be what? 1 ohm. Clear? It is defined from here only. Got it? When 1 volt, okay, if the potential difference between the two ends is maintained at a difference of 1 volt, and if that conductor through it, if 1 ampere of current flows through it, then that material is said to have 1 ohm resistance. Got it? Yes. Now from this expression we see that your I, current, can be expressed as B by R. So your current and resistance, they are inversely proportional. So when resistance is very high, current will be very, very small, inversely proportional. When one is high, other will be low. Got it? That is what it is said. When your resistance is double, then your current will get half. Okay? Yes. Now let's see the factors, various factors on which this resistance of a conductor depend. Resistance, as I told you, that it is a proportionality constant and it depends upon the dimension, length, breadth, cross-sectional area, temperature, material, right? So we need to see on what factors this resistance of a conductor depend. At a particular temperature for a particular material, okay, your resistance is directly proportional to the length. Longer the length, more will be the opposition. That means opposition means resistance will be high. So your resistance is directly proportional to the length of the conductor. Got it? Longer the length, more will be the opposition to the flow of that electric current. So your resistance is directly proportional to the length. Your resistance is inversely proportional to the cross-sectional area. Got it? 1 by A. This is not I, okay? This is length, small l. So your resistance is directly proportional to the length L. Your resistance is inversely proportional to the cross-sectional area. So we can simply write R is equal to combining these two. Okay, combining these two, R is directly proportional to L. R is directly proportional to L. R is directly proportional to 1 by A, where A is a cross-sectional area. You can also say that R is inversely proportional to the cross-sectional area. So combining these two, you can write R is directly proportional to L by A, right? So if you want to change this proportionality into equality, then your constant of proportionality comes up. And that constant of proportionality we denote it by rho. What is this rho? Rho is a constant of proportionality known as resistivity of that material. And this resistivity of the material is also known as what? Specific resistance. I will tell you the reason why it is known as specific resistance. Okay. Now, rho is what? Constant of proportionality known as what? Resistivity of the material of the conductor, which is independent of the dimension of the conductor but depends on temperature. This is very important. It is independent of what? The dimension, length, breadth, thickness, cross-sectional area. It is independent of all those things, but it depends upon temperature. Higher temperature, more will be the resistivity. Resistivity also depends upon the material also. Resistivity will have different values for copper. It will also have a different value from that of what? Iron also, gold also. It will have a different values for different material. So if you know that particular material is coming out to be a fixed value, say suppose a non-value, then we can compare that non-value with a table. Then you can easily find out what material is that conductor. We can easily find out by knowing that what? Resistivity. Now resistivity, as I told you, that it is also known as specific resistance. If you try to express this rho, then rho will be equal to what? Rho will be equal to RA by L, right? So if you take it that L is equal to 1 meter, A is equal to 1 meter square, then your rho will be equal to R. When what? L is equal to 1 unit length, 1 unit length, got it? L is equal to 1 unit length, and your cross-sectional area is equal to also 1 unit area. In SI unit, it will be 1 meter square, and this will be of 1 meter. So if these two are equal to 1 each, then your rho will be equal to R. So your resistivity may be defined as what? Resistance offered by what? Offered by a conductor of unit length, got it? Of unit length, having unit cross-sectional area, got it? So that resistance offered by a conductor of unit length having unit cross-sectional area, that resistance is known as what? Resistivity. That's why we call it as specific, for specific length, for specific cross-sectional area, got it? So that resistance offered by a conductor having unit length and of unit cross-sectional area, we call it that as what? Resistivity. So that's why we call it this resistivity as specific resistance. Specific unit, specific length, unit cross-sectional area. That is also unit or specific cross-sectional area. So if you happens to have that a cube, a unit cube like this, unit cube means of each side will be of 1 unit length. This also unit length, unit breadth, unit height also, got it? So the resistance offered by a unit cube of the material, we can also say that it is what? Resistivity. So resistivity can be defined as the resistance offered by a unit cube of the material. We call it that also as what? Specific resistance. And its SI unit will be what? Ohm meter. Your SI unit of resistance is measured in ohms. SI unit of area will be what? Meter square. SI unit of length will be what? Meter. So 1 meter and 1 meter will cancel and you will have ohm meter. Okay, so SI unit of resistivity will be what? Ohm meter. Got it? Yes. Let's clear it all these things and let's go further. Okay, the SI unit, as I told you, that resistivity SI unit is what? Ohm meter. So it will have different values. Okay, your conductor is having list and its resistivity, that means resistivity of the conductor will lie between 10 to the power minus 8 ohm meter to 10 to the power minus 6 ohm meter. Okay, from 10 to the power minus 8 ohm meter to 10 to the power minus 6 ohm meter, that means this will be that of what? Conductor or metal. And if it is that of an insulator, then it will be very high and its value lies between what? 10 to the power 12 ohm meter to 10 to the power 17 ohm meter. Got it? Now let's go to that of the connection of resistors. Okay, there are two types of connection of resistors. Generally we call it that as two, rather it should be three. Okay, and we will learn only about these two, rather in the practical life it will be having three. Okay, the two mode of connections in the resistors are what? Series connection and parallel connection. The other third one, that will be known as mixed connection. Okay, now series resistors in series, what happened? This every resistor has two terminals. Okay, if you connect one after the another two or more resistance, then we call it that type of connection as series resistors. Okay, here also you will see that there are three resistors, R1, R2, R3, and they are connected one after the another like this, one after the another. Okay, and there will be two terminals here at the two ends. Got it? And if this 2N is connected to the source of EMF like this, okay, with the ammeter and voltmeter like this, then what happened? We will call it such type of connection of resistor as what? Series connection. You will see R1 here, R2, R3, and the potential difference here is measured for the two ends of the what terminals of this A and B. But if you want to measure the potential difference, okay, across this R1, then your voltmeter should be connected here like this. Got it? So this potential difference between these two terminals, or rather across R1, will be denoted by V1, and that potential difference across what? R2, it is denoted by what? Your V2, and that across what? This R3 is denoted by V3. V1, V2, V3 are the potential difference across R1, R2 and R3 respectively, and let the current flowing here be denoted by I. Okay, and the special property that is having in the case of series connection of resistor is that the same current, okay, the same current flows across R1, across R2, across R3 also. Same current will be flowing. Got it? Even though the opposition offered by them are all different. Okay, if they are connected in series, then the current flowing through them will be of same value. If 1 ampere is flowing here, then 1 ampere must be also flowing, 1 ampere must be also flowing here. Okay, that is the first special properties. And the second special properties of this series connection is that the sum of the potential difference V1, V2, V3 across these different resistors will be equal to the total potential difference across the two ends of that connection of resistors in series. Okay, so your V1 plus V2 plus V3 will be equal to V, the potential difference across this series connection, and that will be also equal to the potential difference here at the two ends of the battery. Okay, that is the special property of what? That are the special properties of what? Series connection. Got it? So in the case of series connection, I am repeating again, same current flows across different resistors connected in series. Got it? The second one is what? The sum of the potential difference across different resistors will be equal to the total potential difference. Got it? So these are the special properties of series connection, and let's try to find out the equivalent resistance. What is this equivalent resistance? Let me tell you first. If two or more resistance, okay, connected in a circuit like this, if it can be replaced by a single resistor, then that single resistor is known as equivalent resistance or resultant resistance of these two or more resistance connected in series. Okay, if it can replace these three by a single resistor, then that single resistor is known as resultant resistor of these three, or you can also call it as resultant resistance or resistor. Okay, let's see that part. Okay, yes, so these are connected in series R1, R2, R3 as we have done in that previous one. Okay, so your total potential difference B will be equal to B1 plus B2 plus B3 as I said, right? Yes, this is the one. Or if you try to express this B1, then that will be equal to B1 will be equal to, by your Ohm's law, it will be equal to I times R1, because B is equal to IR from your Ohm's law, right? So your B1 will be equal to the current that is flowing through this is I, and its resistance is R1. So your B1 will be equal to I times R1. Similarly for B2 also it will be I times R2. B3 will be equal to I times R3. That is what, okay, it is having. But if you are having these three resistance, if it can be replaced by a single resistance, so let's take it that as R, and this R will be called as equivalent resistance. Now we replace it those three by a single resistor. So this single resistor R will be called as what? Yes, resultant resistance or equivalent resistance of that three, R1, R2, R3, right? Then what happened? The current flowing here will be also the same current. The potential here will be also same V, right? So we can express this V as what? I times R. That is what I have done here. Got it? For that B1, I1 times R1, B2, I2 times I times R2, B3 will be equal to I times R3. So for this B also it will be equivalent to I times R, right? So we replace it like that. So after cancelling I from the both sides of the equations, then you will get it like this, right? So if you replace this equivalent resistance instead of R by RS, so as to make you understand that this is the equivalent resistance for series, RS, okay, so let's denote it this R by RS, because this is the equivalent resistance of resistors connected in series. So your RS will be equal to R1 plus R2 plus R3 like that. Okay, got it? So in this series connection of resistor, your equivalent resistance is equal to the sum of the resistance of the individual resistors. Okay, if there happens to be another fourth one, R4, then there should be coming as plus R4 here. Got it? So your equivalent or resultant resistance is equal to what? Sum of the individual resistances. Got it? So from this we can say that this R1 will be less than R2, RS, I mean R2 or R3. Okay, either R1, R2, R3, this will be surely less than RS. Got it? Or rather you can say equivalent resistance will be greater than either of these individual resistances. Got it? Now let's see about the parallel connection. Okay, in the case of parallel connection, what happened? Resistors having two terminals will be connected one side to the other terminal. Okay, other terminals, one terminals will be all connected to one point. The remaining terminals will be connected at one point. Got it? So if such type of combination or connection happens in the case of resistor, then we call it this as parallel type of connection. Okay, or parallel combination of resistors. Got it? And then source of EMF is connected like this through the battery, and then plug key, ammeter here in the series, and voltmeter in parallel like this. Got it? So now the special property in the case of this parallel connection is that different current will flow, no doubt, depending upon how much opposition are offered by these resistances R1, R2, R3. But here the same potential will be there across the different resistors. Okay, the potential difference B will be also the potential difference for R1, for R2, and for R3. Got it? So same potential difference across the different resistors. In the case of series, that was same current flowing. Here same potential difference across different resistors connected in parallel. But again, there in the case of series connection, the total potential difference is equal to sum of the potential difference across the different resistors. V is equal to V1 plus V2 plus V3, right? But here in the case of parallel connection, total current will be equal to the current flowing, the sum of the current flowing through different resistors. So your I will be equal to I1 plus I2 plus I3. That is the second special property for parallel connection. Got it? The total current is equal to what? Sum of the current flowing through different resistors. The second property is what? The total current is equal to the sum of the current flowing across or through the different resistors. What was the first property? Same potential difference across the different resistors. Okay? Yes. Now if we happens to write this I is equal to, okay, from your Ohm's law, V, the potential difference across R1, this will be equal to V will be equal to I1 R1, like that. Now if you want to write I1, then your I1 will be equal to V by R1, right? So let's try to change one by one for these I1, I1, I2, I3. Got it? Let's see, like this. Got it? In the same way, if I'm going to replace the three resistors by a single resistor, then the equivalent circuit will be like this. Got it? So that I will also replace, instead of I here, instead of I will have to replace it, the current I that is flowing here, that current I will be equal to what? V by R, right? Where V is the potential difference across this equivalent resistance R. So your I will be equal to V by R. That is what I have replaced it for this one. Okay. So by cancelling your VV from both sides of the equation, then what happened? You will get it. Then you will get it what? 1 by R is equal to 1 by R is equal to what? 1 by R1 plus 1 by R2 plus 1 by R3. So similar to that, in the case of series connection, we replace it this equivalent resistance R by RS. Here also in parallel, let me replace it R by R parallel. Okay, RP I mean. So your 1 by RP is equal to 1 by R1 plus 1 by R2 plus 1 by R3. We simply say that reciprocal of the equivalent resistance connected in parallel will be equal to sum of the reciprocals of the individual resistors. Okay. You have to be very cautious that in the examination, okay, many of the students try to write like this: RP is equal to 1 by R1 plus 1 by R2 plus 1 by R3, like that. This is wrong. Got it? Where lies the fault? Instead of this RP, you have to write 1 by RP. Okay, don't try to write RP alone. It should be 1 by RP will be equal to what? 1 by R1 plus 1 by R2 plus 1 by R3, like that. Okay, don't forget it, this one. Next, let's try to move on to the next one, and I will try to show you the actual diagram how to be connected in the case of the bulb and a battery for this series and parallel. Okay, let's see. So in the case of series connection, see, this bulb has its own filament. It's just like a resistor. Okay, in that way, what happen if you connect it one end of this, okay, resistor or bulb to the other, and so on. If you keep on going, then we will call it as series connection. the schematic diagram will be like this. Okay, in the case of parallel, see the two terminals are connected at one point, the remaining terminals are connected at one point. Then we will call it this as parallel type of connection. Okay, now let's go to the another important topic known as heating effect of electric current. You know that when current passes through the conductor, okay, having some resistance R, okay, then what happen, due to this motion of these free electrons, what happen, heat will be generated. From where that heat is generated? Because this source of EMF try to move against the opposition that is offered by the conductor here. So in doing so, what happen, this cell need to do some work, okay, in trying to move against that opposition. So some work must be done. So that much amount of work done, okay, in transferring those charges from low potential to high potential, okay, that amount of work done will be produced or generated in the form of heat. We know that your electric potential, you read the descriptions, or if you want to note down, you pause this video and you try to note it down, okay, but let me not read all those texts word by word, okay, but let me explain you, okay. Now, as I said, what happened? This electric potential, how do we define electric potential? We define electric potential as the amount of work done in bringing a unit positive charge from one point to the another point inside the conductor. So we define electric potential as what work done per unit charge, like this, right? So that much amount of work done, as I told you, in trying to move or push this charge from the low potential to the high potential, what happened? This electron has to do some work against that opposition. Got it? That much amount of work done, that is nothing but that is W, and this W is equal to V into Q. Got it? So your V into Q is the amount of work done which will be converted in the form of heat. So your height will be equal to V into Q, where this Q can be expressed as what? From that expression of current, current is defined as rate of flow of charge. So your Q will be equal to IT, right? So your Q will be equal to I into T. Your Q will be equal to I into T. So let me write as, instead of Q, let me write as IT here. Got it? So what is this T then? This is the amount of time that is flowing by the current through that conductor. Okay, longer the time, more will be the heat developed. Got it? So your heights can be expressed as what? V is equal to what? IR from your Ohm's law. V is equal to IR. So if you replace it, this V by IR, then it will be IR into IT, right? So I square RT. So this is the expression of heat produced or developed through this resistor when current I flows through it, okay, for a time T having resistance R. Got it? So what happened? This height's amount of heat developed or produced is directly proportional to the square of the current. Got it? Square of the current. So what happened if your current is changes 3 times? Then what happened? Your heat developed will be what? 9 times. If your current changes by 4 times, then it will be what? Square 4. Square means what? 16. So your heat will be more and more. Okay. So that means what? Heat will be what? 16 times in that case, right? So we need to check it, this amount of current. If you don't want to waste the amount of electrical energy in the form of heat, then we need to try to lower this amount of current. That is done in the case of transmission of this what? Electric power from one end to the another end, okay, by using what? By using your AC current, which we make it that to lower the amount of current by using what? Your transformer. Got it? That is happening in the case of HT lines, high tension lines, okay. So let's see those expressions, okay, one by one, as I have done there. So it will be coming up here. You pause it and you try to copy down if you want. Okay, this is the equation of the amount of heat produced when the current I flows through the circuit, okay, through the conductor having resistance R for a time small t. Got it? Yes. Let's go to the next one. That means electrical energy and electric power. We have done that one. Just in the case of that of the amount of heat produced. That amount of heat produced is nothing but that is the amount of work done in transferring that charge from one point to the another point having potential difference V. Got it? So this is nothing but this is the amount of work done. That amount of work done, okay, we call it that as what? Electrical energy. Work and energy are interconvertible, right? So electrical energy, it is nothing but it is the work done to maintain the flow of current in a conductor. Okay, if there is no work done, then your electron will not able to flow through that conductor. Okay, as some work is done, that work done, we call it that as what? Electrical energy. Got it? Its SI unit will be what? Joule, right? Electric power is nothing but it is a rate of energy consumed or energy produced. We call it that as electric power. So rate, if in the denominator time is there, then we usually use rate in physics. Okay, rate of doing work, because work done per unit time, we call it that as rate of doing work, and that rate of doing work we call it as power. So power is equal to what? W by T, where W is a work done. Okay, this work done will be equal to what? Energy consumed. In the case of your consuming end, just like that in your house, electric bulb, electric heater, so we call it that amount of energy consumed as work done. Okay, and in the case of generating end, suppose in the case of that of generator, in the case of power plant, the energy is going to be what? Produced there. So in that case also, the amount of energy produced or work done, okay, that will be in the numerator here divided by time. You will get it that as power. So work done may be defined as a rate of energy produced or energy consumed. Okay, we call it that as power. So as we know that W is equal to I square RT, so by putting all those expression here, W is equal to I square RT, T cancel, and you will get it as what? I square R. So this is also one of the expression of power. You can also express this B, okay, I square R, you can write as I into I like this, so that what happen, your one of your using your Ohm's law, that V is equal to IR, we can express another form of power as V into I or I into V. Got it? And if you express this V by using your Ohm's law again, okay, then what happen, your V power will be equal to V square by I. I means what? V by R, na? So V square in the denominator R there, so V square by R. It should be V square by R, not V square R, okay? You just corrected this one. This should be V square by R. Got it? Yes, not V square R. Clear? So these are the expression of what? The power, okay? So you need to remember this different expression. Power is equal to I square R. Power can be expressed as V into I. Power can be expressed as V square by R. Got it? And the SI unit of power is what? Watt. Okay? 1 watt is the power consumed when 1 ampere of current flows across a potential difference of 1 volt. We are defining from where? From where this we define it? We define it from here only. Got it? If this is going to be 1, then this 2 must be also 1. So if it is going to be 1 watt, this current should be 1 ampere, this potential difference should be also 1 volt. So 1 watt is the power when 1 ampere of current flows across a potential difference of what? 1 volt. Got it? There are some bigger units of power. This 1 watt is a small power, so the bigger units are what? 1 kilowatt. kW, kilo means 1000, okay? So 1 kilowatt will be equal to 1000 watt, 10 to the power 3 watt. 1 megawatt, capital M means mega, that means 1 million, okay? If I write this small m, then it will be 1 milliwatt, 10 to the power minus 3, okay? but this is capital M, so it is megawatt. MEGA, megawatt. 1 megawatt will be equal to 1 million watt, that is 10 to the power 6 watt. Okay, now another important one, the commercial unit of energy is what? 1 kilowatt hour. Okay, so this 1 kilowatt hour, it is generally asked to express in terms of joule. So this 1 kilowatt hour is nothing but this is the energy consumed or produced when a power of 1 kilowatt uses for 1 hour. Okay, right? So if a power of 1 kilowatt, if it is uses for 1 hour, then the amount of energy consumed, we call it that as 1 kilowatt hour. Got it? So your 1 kilowatt, kilo means 1000, and this hour you change into what? Seconds. Then if you cross multiply it, and if you try to if you multiply it and if you try to keep in the standard form, then your 1 kilowatt hour will be equal to 3.6 into 10 to the power 6 joule. Okay, this is generally asked, okay, in the examination. Express 1 kilowatt hour in joules. Got it? Then you have to do this one, and then it will be just 1 kilowatt hour will be equal to 3.6 into 10 to the power 6 joule. So the commercial unit is what? 1 kilowatt hour, as I said here. And again, 1 kilowatt hour can be defined in this way. 1 kilowatt hour is the energy consumed when power of 1 kilowatt. Okay, instead of this 1 watt, you have to write as 1 kilowatt. Okay, when a power of 1 kilowatt uses for 1 hour. Okay, that much amount of energy consumed by a power, okay, by an electrical appliances having power of 1 kilowatt. If it uses for 1 hour, then that amount of energy consumed by it will be known as what? 1 kilowatt hour. Got it? With that, we come to the end of our today's class. Thank you.